Hello students, I hope you all are doing good. So today we are going to discuss alternating current NCRT section 7.8, example 7.8 to 7.10. This is the disclaimer. So after this lecture you will be able to calculate resonant frequency and its effect on circuit performance, understand power delivery at resonance and study transformer principle and losses. Okay, so today we are going to discuss one very important topic, that is transformers. Okay, very important topic from the point of competitive exams. Okay, and also we are going to discuss three examples. Yesterday we have discussed the power factor. Based on that topic we are going to discuss some examples, then we are switching to transformer topic. So index of topics that we are going to discuss today is example 7.8, example 7.9, example 7.10, and NCRT section 7.8 transformers. So let's begin with example 7.8. So a sinusoidal voltage of peak value. Now it is mentioned in the question. So we have discussed that if it is not mentioned which value is this, we have to take the RMS value. But if it is mentioned that it is peak value, so you have to take it Vm. Okay. So this value of voltage is peak value 283 volt. Okay. And frequency 50 hertz is applied to a series LCR circuit in which R equal to 3 ohm, L equal to 25.48 millihenry, and C equal to capacitance is 796 microfarad. Okay, you have to find A, the impedance of the circuit, B, the phase difference between the voltage across the source and the current, and C part you have to find the power dissipated in the circuit, and D part you have to find the power factor. Okay, so let's see how we will do it. So firstly you have to list all the given things. What is given in the question? Vm is given, maximum value of voltage, which is 283 volt. Frequency of AC current or AC voltage is given, nu equal to 50 hertz. Resistance R is given 3 ohm, L is given 25.48 millihenry, and capacitance and we have to convert it into SI unit, 25 into 0.48 into 10 to the power minus 3 Henry, and capacitance is given 796 microfarad, and in SI unit it can be written as 796 into 10 to the power minus 6 farad. Now A part, to find the impedance of the circuit we need to calculate the XL and XC first. Okay, so what is the expression for impedance? Z equal to root R square plus XC minus XL whole square. Okay, so we need to find the we are given with value of R. We have to find the XL and XC first. So calculation of XL. So XL is equal to omega L, and omega is 2 pi nu. So we can write XL as 2 pi nu L. NCRT question 7.13. So XL will be equal to 2 into pi 3.14 into what is nu 50 hertz into L, and what is L 25.48 into 10 to the power minus 3. Okay, so XL is equal to 8 ohm. Okay, so now calculation of XC. Yeah, now we have to calculate the XC. XC is equal to 1 by omega C. So omega is 2 pi nu. So we can write XC as 1 by 2 pi nu C according to NCRT equation 7.17. Now put the values. XC will be equal to 1 by 2 into pi is 3.14 into nu is 50 into C is 796 into 10 to the power minus 6 farad. Okay, so after solving it, XC will be equal to 10 to the power 6 upon 249944. Okay, so XC will be approximately equal to, after solving and simplifying it, XC will be approximately equal to 4 ohm. Okay, so you can take approximate values to make the calculation simpler, because calculators are not allowed in the exams. So you, if the value is coming in decimals, you cannot find it, you cannot square it, you cannot take the root of it. Okay, so to simplify the calculations, you can take the nearby round of value. So now we can calculate the impedance. So impedance is given by root R square plus XL minus XC whole square. Okay, according to NCERT equation 7.26. So R is given 3 ohm, and XL we have calculated 8 ohm, and XC we have calculated 4 ohm. So 8 minus 4 will be 4. So Z will be equal to root 3 square plus 8 minus 4 square, which is 4 square. So 3 square plus 4 square will be equal to 16 plus 3 square, sorry, 9 plus 16. It will be 25. So root 25 will be equal to 5. So Z will be equal to 5 ohm. Okay, so we have calculated the impedance. Now B part, we have to calculate the phase difference between the voltage across the source and the current. Now calculation of phase difference. So we know that tan phi is equal to XC minus XL upon R. Okay, so you can write it as phi equal to tan inverse XC minus XL upon R. Okay, if you are not able to understand the inverse function, you can simply write it as tan phi equal to XC minus XL upon R. Okay, no need to bother this inverse function also. Okay, so NCERT equation 7.27, and phi is equal to tan inverse 4 minus 8 upon 3. Okay, which is equal to tan inverse 4 minus 8 will be minus 4. So minus 4 by 3. So tan inverse function will omit inverse out of its argument. Okay, so minus 4 by 3, minus will come out of the angle part, this argument of tan inverse. Okay, or if you are going to solve it by using tan phi equal to XC minus XL upon R. So tan phi will be equal to minus 4 by 3. Okay, so minus 4 by 3, what is the value? So you have to remember two values for tan phi. So tan 53 degree is equal to 4 by 3, and tan 37 degree is equal to 3 by 4. Okay, these two values you need to remember. These two values are being used in various chapters. Okay, so you have to remember these two values of tan. Tan 53 degrees 4 by 3, tan 37 degrees 3 by 4. Because we generally use this configuration of Pythagoras theorem 3, 4, 5. Base 3, 4 perpendicular, and 5 is hypotenuse. We use this triangle or configuration of right angle triangle very much in physics chapters. Okay, so that's why tan 53 degree you have to remember, and tan 37 degree you have to remember. Okay, so if tan phi is equal to minus 4 by 3, so minus 4 by 3 will be tan 53 degree. So tan phi is equal to minus tan 53 degree. So it will be, so by equating both these, we can write phi is equal to minus 53 degree. Okay, or by inverse function, we can write phi is equal to minus tan inverse 4 by 3. So tan inverse 4 by 3 will be 53 degree, or it is approximately 53 degree, but actually it is 53 point something, which we can write 53.1 degree. Okay, you can write 53, it will be okay only. 53 is also correct option. Okay, so phi will be equal to minus 53.1 degree. So it is negative. That means current is lagging behind. Okay, so phase difference is negative in the case of inductor. Okay, now as XL is greater than XC, phi is negative. We have also seen that XL is 8 and XC is 4. So inductive reactance is more. That means which type of circuit is this? Inductive circuit. This is inductive LCR circuit. That means phi will be negative. Current will lag behind. Okay, so XL greater than XC, phi is negative, and current in the circuit will lag the voltage across the source. Okay, now C part, average dissipated power in the circuit we have to calculate. So P equal to IRMS square R. We need to find IRMS first. So Im is equal to Vm upon, so this is the expression for peak values. Okay, so maximum value of current will be equal to Vm upon Z according to NCERT equation 7.25b. Okay, we know that if we IRMS will be equal to Im upon root 2. This is like relation between IRMS value of current and peak value of current. So IRMS is equal to Im upon root 2. Put the value of Im in this expression. So Im is, according to NCERT question 7.25b, Im is Vm upon Z. So IRMS will become Vm upon root 2Z. Okay, so now put the value of Vm. Vm is given 283 and Z we have calculated 5, impedance 5 ohm, and root 2 is there. So IRMS is equal to 283 upon root 2 5. So it will, after solving it, it will come out to be IRMS will be equal to 40 ampere. Okay, so we have calculated the IRMS value. Now we will calculate the average power dissipated in the circuit. So calculation of average power dissipated in the circuit is given by P equal to IRMS square R. So therefore average power P will be equal to what is IRMS 40 we have calculated, and what is R 3 ohm. So IRMS square into R. We know that average power formula is IRMS square Z cos phi, and cos phi is R by Z. So Z in the numerator and denominator will cancel out. It will become IRMS square R. Okay, actual formula is IRMS square Z cos phi. Cos phi is R by Z. So Z and Z will get cancelled out. It will become IRMS square R. Okay. Now P is equal to, after solving it, 4800 watt. So this is the expression for, and this is the value for average power. Now we will calculate the power factor. Power factor is defined by the cosine of phase angle. Okay, what is the phase difference or phase angle? We have calculated phi is equal to minus 53.1 degree. So power factor is cos phi, which will be equal to cos 53.1 degree minus 53.1 degree, and power factor is equal to, so cos 53.1 degree will be equal to 0.6. Also we can calculate the cos value. Cos phi is equal to R by Z. What is R? 3. What is Z? 5. Okay, so what is cos phi? Cos phi is equal to 3 by 5. In simple words, we can find cos phi with the help of its formula, that is R by Z. Cos phi is R by Z. R is 3 ohm, Z we have calculated 5. So 3 by 5 is 0.6. Okay, you can, this is the simplest way. Or you can find using angle. We know the angle minus 53.1. So cos minus 53.1 degree is equal to 0.6. So power factor of given series LCR circuit is given by 0.6. Now next example 7.9. Suppose the frequency of source in previous example can be varied. That is A, what is the frequency of the source at which resonance occurs? B, calculate the impedance, the current, the power dissipated at resonant condition. So let's see what is the solution. So in the previous example, suppose the frequency of the source is varied. Okay, so firstly we have to calculate what is the frequency of source at which resonance occurs. So from previous example, what is given in the previous example? L equal to 25.48 millihenry, which is equal to 25.48 into 10 to the power minus 3 henry, and C is equal to 796 into 10 to the power minus 6 farad. Now A part, the frequency at which resonance occurs. We know that at resonance XL is equal to XC. Inductive reactance become equal to capacitive reactance. Okay, so due to which XL is equal to XC, we have derived this expression. I am telling you again. So XL is omega L, or we can write omega naught L at resonant frequency, and XC at resonant frequency we can write 1 by omega naught C. So after equating it and rearranging, it will become omega naught will be equal to 1 by root LC, according to NCERT equation 7.28. So this expression came from equating capacitive reactance equal to inductive reactance. So after putting the values, so omega naught is equal to 1 by root 25.48 into 10 to the power minus 3 into 796 into 10 to the power minus 6. So omega naught is equal to 10 to the power 5 upon root 2028.2. Okay, so omega naught is equal to 10 to the power 5 upon root 2028.2. So after solving it, omega naught came out to be 222.1 radian per second. Okay, so angular resonant frequency omega naught is 222.1 radian per second. So we have to calculate the resonant frequency, not angular frequency. We have calculated the angular frequency. Now how we can find the frequency? So linear resonant frequency can be calculated using the expression omega naught is equal to 2 pi nu naught. So we know that omega is equal to 2 pi nu. So omega naught, following the conventions or following the notations for resonant frequency, it is omega naught is equal to 2 pi nu naught. So nu naught will be the frequency of source at resonance. So omega naught nu naught will be equal to omega naught upon 2 pi. So after putting the value omega naught, we have calculated 222.1 radian per second upon 2 into pi is 3.14. So after solving this, nu naught will be equal to 35.4 hertz. So this is the frequency of source at resonance. Hence resonance in circuit will occur at frequency 35.4 hertz. So if it is asked that you have to find the angular frequency at resonance, so omega naught will be there. Okay. If it is asked only frequency, so you have to calculate the nu naught also. Now B part, you have to calculate the impedance. So impedance Z at resonance, we know that at impedance XL become equal to XC. So XC minus XL will be equal to 0. Because both are equal, so difference of both these reactance will be 0. So Z will be equal to root R square, which is equal to R. So at resonance or at resonant condition, impedance Z is equal to the resistance, which is Z equal to R equal to 3 ohm. So at resonance, Z equal to R, and RMS current will be equal to IRMS equal to VRMS upon Z, which is equal to VRMS upon R, because Z is equal to R. So IRMS will be equal to 283 upon root 2. Okay, so in previous question, it was given V maximum peak value of voltage was given, which was equal to 283 volt. Okay, so RMS value of voltage will be peak value upon root 2. So this is done by that concept. So this 283 was peak value, Vm. So VRMS can be calculated by Vm upon root 2. So this is the value of VRMS, 283 upon root 2, and R is given 3 ohm. So 283 upon root 2, 3. So RMS current can be found using this formula. So IRMS will be equal to 66.7 ampere. Okay. So what will be the power dissipated at resonance? So power dissipated will be equal to IRMS square into R, which was equal to RMS we have calculated 66.7 ampere, and resistance is of 3 ohm is given. So 66.7 square into 3. So P is equal to power dissipated at resonance is equal to, that is also called maximum power dissipated at resonance. So P is equal to 13.35 kilowatt. So this is the power dissipated at resonant condition. So power dissipated in the previous case was, so in previous case when there was no resonance, power dissipated was 4.8 kilowatt in previous question. This means power dissipated at resonance is more than as compared to the other frequencies. Okay, and also we have discussed that power dissipated at resonance is maximum. Now, next example 7.10. At an airport, a person is made to walk through the doorway of a metal detector. Okay, you may have seen at metro stations or at airport. Okay, at metro station and uh, at any venue where gathering is more. Okay, or on certain railway stations also. Okay, like Delhi railway station, not common railway stations, but like capital or in district. So their metal detector was inserted. So at an airport, a person is made to walk through doorway of a metal detector for security reasons. If he is carrying anything made of metal, the metal detector emits a sound. On what principle does this detector work? Okay, so we will discuss how this metal detector is working. Okay, so this is the example from daily life. Okay, let's see. So metal detector works on the principle of resonance in AC circuits. When we walk through a metal detector, we are in fact walking through a coil of many turns. Okay, so that metal detector, it is a closed path. You may have seen uh, on the bottom part, it is also the base and a complete door like structure is made. Okay, so this is a closed loops. Okay, so when we walk through a metal detector, we are in fact walking through a coil of many turns. Okay, coil is connected to a capacitor tuned so that circuit is in resonance. So this coil of many turns through which we are moving, okay, that doorway, okay, that is made of a coil of many turns that is connected to a capacitor which is tuned at a resonant condition. Okay, so circuit is in resonance when we are not moving through it. That coil of many turns are behaving like inductor. We know that inductor is made up of coil of many turns. So that doorway which is consisting of coil of many turns behaves like an inductor. Okay, so this coil is connected to a capacitor. So it is like series LC circuit. So coil is connected to a capacitor tuned. So this circuit is tuned at resonance. When we walk through it, so inductance L of a coil changes. So we are moving through this doorway, through this coil. If we are carrying anything made of metal, so we are inserting some metal object inside the inductor, due to which inductance of the coil changes. We have discussed that if we are inserting any core material inside the windings of the inductance of the inductor changes. So if we are carrying something made of metal through the coil of many turns, so inductance or L of a coil changes when a metal is inserted in it, which results in change in impedance. So if L is changing, XL will change, which is equal to omega L. If XL is changing, impedance will change. Okay, which results in change in impedance of a circuit as XL is equal to omega L. When we walk through the metal in your pocket, okay, any key or anything made of metal you are carrying, so impedance of the circuit changes, resulting in significant change in the current in the circuit. So that resonant condition is disturbed. Circuit is set to a resonance, but that resonant condition is disturbed because L is changed, XL is changed, due to which current in the circuit will change. And the setup is made up of something, some mechanism that if current is changing, if resonance condition is disturbed, then that electronic circuitry causes a sound to be emitted as an alarm. So it will emit a sound. So this is the principle of metal detector. So this change in current is detected and electronic circuitry causes a sound to be emitted as an alarm. Okay, so resonance condition is disturbed, current in the circuit is changed, due to which alarm sound is emitted. Got it? Now, transformers. Our NCRT section 7.8. So for many purposes, we have discussed in our previous classes that voltage can be stepped up or stepped down. We have discussed many times that we can change the voltage to decrease the power loss in the transmission lines. Okay, I have mentioned there also that we are going to see in the upcoming lectures, that how we can change the voltage and current in the transmission lines, or how we can step up or step down the voltage. So here is the concept transformers. So for many purposes, it is necessary to change or transform an alternating voltage from one value to higher or lower value. So we have to change for many reasons, for many purposes, we have to change the voltage, alternating voltages. Okay, so we know that in transmission lines, the value of voltage is around 1100 voltage, or in transmission lines of big, very very large poles, when we are transmitting electricity from one state to another state, okay, very large poles are used. Okay, and voltage uh, or potential difference across these transmission lines are somewhat 11,000 volts. Okay, very much higher voltage is used. But when we are operating any devices at home, Okay, they are using voltage supply of 220 volt. So here transformers are needed. That's why transformers are inserted. They are what they are doing at power generation stations. They are stepping up voltage for transmission, and at receiving stations they are stepping down the transformer to a safe, means less harmful or less dangerous voltage limits. So this is done with the device called transformer using the principle of electromagnetic induction and mutual inductance. Transformers is basically a voltage control device that is used widely in the distribution and transmission of alternating current power. Okay. General purpose of using transformer is to maintain a balance between electricity that was generated at very high voltages. Okay, we generate at generating stations where power is being generated. They are generated or transmitted at very high voltages, and where we are going to use it or consume it, and at consumption stations or consumption sites, which is done at very low voltages. Okay, what is consumption sites? Our homes. We are using electricity at very low voltage ranges at 220 volt, but in power lines it is about 1100 voltages. Okay, so transformer is basically a voltage control device. Okay, it is controlling voltage, it is stepping up or stepping down voltage. So what type of transformers that we see near our homes? That are step down transformers. Okay, they decrease the voltage from high value to low value. Okay, so construction of transformers. So this is the diagrammatic representation, figure 7.16. Two arrangements for windings of primary and secondary coil in a transformer. A, two coils on top of each other like this, or we can uh, wind the coils in second arrangement also. Two coils in separate limbs of the core. Okay, in two arrangements, in these two arrangements we can wind the coils. So there are two coils. A transformer consists of two sets of coil insulated from each other. Okay, so there is insulation is being done so that the current flowing through both this uh, primary and secondary coil will not interact. Okay, they will not interact directly. So insulation is also done, and it transformer consists of two coils. One is primary, one is secondary. They are wound on a soft iron core. This is soft iron core, either one on top of each other as shown in the figure 7.16. Either the arrangement can be this as shown in the A figure, and either the arrangement can be this as shown in the B figure 7.16b. One of the coils called primary coil has NP turns, so number of turns will be different for both the coils. Okay, it depends upon that either we are stepping up the voltage or stepping down the voltage. Okay, so which coil will having more number of turns? It is depend on the type of transformer. So one of the coils having called primary coil has NP turns. This is primary coil, and one of the coil is called secondary coil. It has NS turns. Okay, so subscript P is used for primary coil. Subscript S is used for secondary coil. Observe the figure 7.16. Number of turns are different in primary and secondary coil. Often the primary coil is the input coil and secondary coil is the output coil of the transformer. Okay, so we are giving input on the primary coil, and output is received at ends of secondary coil. Okay, so if we are going to decrease the voltage, so high voltage power or high power is given at the primary coil. High voltage current is given at primary coil, and low voltage current is received at secondary coil. If we are going to increase the voltage, so low voltage is given at primary coil and high voltage is received at secondary coil. So this is input is connected to the primary coil and output is received at secondary coil. So working of transformers, let's see. When an alternating voltage is applied to the primary coil, it produces a time varying current. Okay, because current is varying with respect to time. So alternating voltage is applied to primary coil. So it will produce, so alternating voltage will produce time varying current. It is changing periodically. This resulting time varying current produces a time varying magnetic field. Since if steady current is flowing through the coil, it will produce the magnetic field which is also steady. But if current is changing in the coil with respect to time, then it will produce the time varying magnetic field. So this magnetic field is also changing with time because current in the coil is changing with time. If magnetic field is changing with time, so magnetic flux through the coil will also change with time. Okay, so since flux is changing with respect to time, so EMF will be induced in the primary coil. Okay, this time varying magnetic field generates a magnetic flux through the coil, which is varying with time also. If magnetic field is varying with time, so magnetic flux through the coil, what is magnetic flux? It is the number of field line passing through the coil. Okay, so if number of field lines passing through the coil is changing, because magnetic field is changing with time, so magnetic flux will also change with respect to time. This magnetic field would normally spread in space. This magnetic field will normally spread it in the space. But why we are using iron core? What is the function of iron core? So this iron core pulls and concentrates the magnetic field lines into itself and increase the change in magnetic flux so that efficiency of the transformer will be enhanced. EMF induced will be large. That's why we are using iron core. It will pull the magnetic field line towards itself. Why? Because soft iron core is a ferromagnetic substance. Most of the field lines will prefer to flow through it. So iron core pulls and concentrates the magnetic field into itself. Soft iron core has very high magnetic permeability. That means field lines prefer to go through it instead of air. Since this time varying magnetic field get associated with the secondary coil also. So secondary coil is wound on the primary coil. So magnetic flux through the primary coil is linked with secondary coil also. Okay. Since this time varying also in the second case, these coils are wounded very closely. This difference is not so much. They are wounded on the different limbs, but they are very close to each other. Okay, so flux linked with the primary coil is considered nearly equal to flux linked with the secondary coil. And we assume it in this derivation that flux linked with the primary coil is equal to the flux linked with secondary coil. Since this time varying magnetic field get associated with the secondary coil, then according to Faraday's law of electromagnetic induction, it induces an EMF in the secondary coil. Okay, magnetic flux is changing through primary coil and magnetic flux linked with the primary coil due to the mutual inductance principle. Change in current in primary coil, or we can say change in flux through primary coil, will induce EMF in the nearby coil also. So it will induce EMF in the secondary coil also. Okay, according to Faraday law of electromagnetic induction. The value of this EMF depends on the number of turns of the secondary coil. So now, what amount of EMF is inducing in the secondary coil? It depends on the number of turns of secondary coil. Okay, so I will give you an idea before that if number of turns of secondary coil is more than the primary coil, then output voltage will be more. EMF induced in the secondary coil will be more. If number of turns of secondary coil is less than the number of turns of primary coil, then EMF induced will be less. Okay, we are going to prove it in the further slides, but I am giving you an idea in before. I am giving you spoiler. We consider an ideal transformer in which the primary coil has negligible resistance and magnetic flux produced in the core is perfectly confined with it. So these are assumptions we are going to take. Okay, so we consider an ideal transformer in which we consider that all the magnetic flux produced in the coil is confined within, or we can say magnetic flux linked with the primary coil is equal to the magnetic flux linked with the secondary coil. We consider it as ideal transformer in which the primary also, second assumption is primary coil has negligible resistance, so that energy loss due to the heat produced in the winding will be neglected. Okay, if resistance will be more, then current will be less, or we can say power loss or energy loss will be more if resistance is there. So we are neglecting the energy loss by considering that there is a negligible resistance in the primary coil, and magnetic flux linked with the primary coil is nearly equal to the magnetic flux linked with the secondary coil. Also, we assume that flux linked with both the primary and secondary coil is same. That means there is no flux leakage. Okay, so flux linked with primary is equal to flux linked with secondary coil. There is no flux linkage or leakage. Let phi be the flux in each turn in the core and t due to time t due to current in the primary coil when a voltage Vp is applied to it. Okay, so phi be the flux in each turn at time t due to current in the primary coil when a voltage Vp is applied to it. Then the induced EMF or voltage epsilon s in the secondary coil with turns ns is. So induced EMF will be equal to, according to Faraday's law of electromagnetic induction, minus dns minus d by dt. And what is flux through the coil? That phi is the flux through each turn, and ns is number of turns in the secondary coil. This is the EMF induced in the secondary coil, which is equal to minus ns. Ns is constant and flux is changing with respect to time. So d phi by dt. Mark it as 7.31 equation. That is the EMF induced in the secondary coil. This alternating flux phi also induces an EMF called back EMF in the primary coil. So flux is changing through primary coil and secondary coil. Okay, so EMF induced in the secondary coil is due to the rate of change of magnetic flux through the secondary coil due to change in current in the primary coil. This is the principle of mutual inductance. And due to the change in current in the primary coil itself, the EMF will be induced in primary coil itself also. That is called self-induction. Okay, so due to the self-induction phenomenon, there is a EMF induced in the primary coil also. That is known as back EMF. It is given by epsilon p is equal to minus np, number of turns of primary coil, phi by dt, and np is constant. It will come out of the derivative minus np d phi by dt. So this epsilon s is the EMF induced in the secondary coil due to the change in current in the primary coil. But epsilon p is the EMF induced in the primary coil due to change in current in itself also, in primary coil also. So mark it as 7.32 equation. Assuming the primary coil has negligible resistance, this is the assumption, the applied voltage Vp equals the induced EMF epsilon p. Okay, so we are considering negligible resistance. So voltage drop across the loop will be negligible, due to which EMF induced will be equal to the voltage. Okay, what is EMF? EMF is the voltage across any component when there is no current drawn from it. Got it? So if we are considering negligible resistance, so we can neglect the potential drop across it. So that's why applied voltage Vp is equal to the induced EMF epsilon p. So this is assumption. So let Vs is the voltage across the secondary coil. Assuming the secondary coil has open circuit, this is an assumption again. We can assume that secondary coil has open circuit. We are not drawing any current from the secondary coil, due to which potential drop across the secondary coil will be negligible. There is no potential drop across the, means EMF will be equal to, EMF induced will be equal to potential voltage across the secondary. We have discussed the difference between voltage or potential difference and EMF also. Okay, EMF is when there is no current is being drawn from the source, and voltage is when current is being drawn from the source. So EMF is inducing in the secondary coil. If we are using or drawing current from the induced EMF in the secondary coil, then Vs will be taken across the secondary coil. But we are assuming that secondary coil has open circuit, no current is being drawn from the secondary coil, or current taken from it is very small, so that we can neglect the voltage drop due to resistance. Then to good approximation, Vs equals to Es. Voltage across secondary coil will be equal to EMF induced in the secondary coil. So Vs is equal to epsilon S. So equation 7.31 and 7.32 can be written as Vs equal to minus Ns d phi by dt and Vp is equal to minus Np d phi by dt. So we have enhanced the equation. It was before epsilon S equal to this and epsilon P. We have replaced epsilon S with Vs and epsilon P with Vp. Now Vs is equal to minus S d phi by dt and Vp is equal to minus Np d phi by dt. So after taking ratio, so we got Vs upon Vp, voltage across secondary coil upon voltage across primary coil. This ratio will be equal to ratio of number of turns of both coils. Okay, so voltage across any coil is directly proportional to the number of turns of that coil. Okay, so means if number of turns of the coil is more, that means voltage across that coil will be more. So if we want to increase the voltage, we have to make secondary coil with more number of turns than primary coil. And if we want to decrease the voltage, we have to make secondary coil of less number of turns than primary coil. Got it? So Vs upon Vp equal to Ns upon Np. That means voltage across the coil is directly proportional to the number of turns of that coil. Mark it as 7.33 equation. Above relation has been obtained using three assumptions. So what assumptions we have taken? So we have taken that a resistance and current in the primary coil are small. Why we have taken this? Due to which voltage drop across the primary coil due to the resistance in the winding will be negligible. So that we can assume that EMF induced will be equal to the voltage across the primary coil. Second assumption is same flux links both the primary and secondary coil. So we have taken to take the ratio, this ratio. We have assumed that flux link with the primary coil is equal to the flux link with the secondary coil, which cannot, this is only for ideal condition. Okay, in actual condition, in real condition, flux link with the secondary coil will be somewhat less than the primary coil. But we have assumed that for an ideal transformer, same flux links both the primary coil and secondary coil as very little flux escapes from the core. So this is the function of soft iron core. Why we are using the soft iron core? So that flux leakage can be minimized. Current induced in the secondary coil is small. This is also an assumption we have taken, that either secondary coil is an open circuit or current drawn from the secondary coil is very, very small. Taking the case of ideal transformer, that is 100% efficiency, no power loss. Input power will be equal to output power. If there is no power, 100% efficiency, ideal transformer, then input power will be equal to output power. That means P input equal to P output. Since power is equal to current into voltage, so we can write power is current into voltage. So input power, what is in which coil we are giving input? Primary coil. So input power will be due in the input power is given to the primary coil, which will be equal to current flowing through the power primary coil multiplied by voltage across primary coil. So IPVP will be equal to output power. Output power will be current in the secondary coil multiplied by voltage across secondary coil, ISVS. Mark it as 7.34 equation. So from this we can take the ratio. So where subscript P is for primary coil and subscript S is for secondary coil. Although some energy is always lost, okay, no system is ideal. So energy is always lost. This is a good approximation since a well-designed transformer may have efficiency of more than 95%. Now from equation 7.33 is, from equation we have seen in 7.33 equation that Vs upon Vp is equal to Ns upon Np. Now from this 7.34, we can write one more result from equation 7.33 and 7.34. These results are important. These all results are important, which we are on which numericals are based on. So IS, this 7.35 equation, this is the conclusion for transformer. So this ratio IS upon IP, current through secondary coil upon current through primary coil, this ratio will be equal to Vp upon Vs, which will be equal to Np upon Ns. That means voltage across any coil is directly proportional to its number of turns, but current through any coil is inversely proportional to the number of turns through that coil. Okay, so this is the relation between current, voltage and number of turns. This is important equation. So now I and V oscillates with the same frequency as the AC source. That means ratio IS upon IP will be equal to IS upon IP maximum values. So they are oscillating with the same frequency. So we can take the ratio as maximum values also, and we can take the ratio as RMS values also. Okay, we can take the ratio as instantaneous value, maximum value and RMS value. They all are equivalent terms. Where M is for, so in both coils, I and V oscillate with the same frequency as the AC source. So where M is for peak value of current and RMS is for root mean square value of current. Similarly for voltage values, if we are taking instantaneous value ratio Vs upon Vp, it will be equivalent to the maximum value ratio. So maximum value of voltage across secondary coil upon maximum value of voltage across primary coil, which will be equal to RMS value across RMS value of voltage across secondary coil upon RMS value of voltage across primary coil. Okay. Now equation 7.35 was IS upon IP equal to Vp upon Vs equal to Np upon Ns. We can write it as 7.35 equation, and from equation 7.35 we can write IS RMS will be equal to Np upon Ns into IP RMS. If we put IS upon IP as equal to IS RMS upon IP RMS that we have discussed, so we can write these equations as these equations. So and Vs RMS will be equal to Np upon Ns Vp RMS. Okay, we can write the ratio of currents or voltages in the term of RMS values only. This is the conclusion. So we can see how a transformer affects the voltage and current. So if the secondary coil has greater number of turns, that I have given you an idea before. If secondary coil has greater number of turns than the primary coil, that means Ns is greater than Np. That means voltage is stepped up. So from this equation, from this 7.35 equation, is if Np is greater than Ns, then Vp will be greater than Vs. If Ns is greater than Np, then Vs will be greater than Vp. So if secondary coil has greater number of turns than primary coil, Ns greater than Np, the voltage is stepped up. Vs RMS will be greater than Vp RMS. Okay, so secondary coil means output will be more than input. That means voltage is increased. That is, voltage is stepped up. This type of arrangement is called step up transformer. If voltage is increased, that transformer is called step up transformer. Okay, however, now current will be having inverse relation with the number of turns. Okay, so however in this arrangement, there is less current in the secondary coil. If voltage is increased in the output signal, then current will be decreased in the output signal. So power is transmitted at high voltage, low current. In transmission lines, voltage is very high, means current is very small. There is less current in the secondary coil than in the primary coil. Means if Np upon Ns is less than 1, then Is RMS will be less than Ip RMS. Now again these equations, if the secondary coil has less turns than primary coil, means Ns is less than Np, it is called step down transformer. In this case, Vs RMS will be less than Vp RMS. So voltage across secondary will be less, means output will be less than input. But output current will be more. Okay. So this is the function of the transformers that we see near our home. They step down the voltage but increase the current. And Is RMS will be greater than Ip RMS. That is, the voltage is stepped down or reduced and the current is increased. Now, there are some energy losses in transformers. So, real transformers are not 100% efficient. Energy is lost due to flux leakage. That we have assumed that there is no flux leakage, but energy is lost in real transformers. There is always some flux leakage, that is, not all flux due to primary coil passes through the secondary coil. So, flux linked with the primary and secondary coil is not actually equal due to the poor design of coil or the air gaps between the core in the core. So it can be reduced by winding the primary coil and secondary coil one over the another. If we wind both coils one over another, it can be reduced to a much extent. But we cannot gain 100% efficiency either by doing this. Resistance of the windings. We have assumed that there is negligible resistance in the windings of primary coil, but there is somewhat significant resistance in the windings. So wire used for winding has some resistance, and so energy is lost due to heat produced in the wire. That is I RMS square R. This is minimized by using thick wires. If we are using thick wire, area of cross section is more, resistance can be decreased, as resistance is inversely proportional to cross sectional area. Another loss, very important, eddy current loss. So what are eddy currents? Eddy currents are loops of currents induced in the surface or bulk of conductors. So they are not induced in the wires. They are induced in the surface. If we are taking any sheet of conductor or a volume or cube of or any solid structure of conductor. So they are induced in the surface or bulk of conductors. They are in the forms of loops, also called as circulating currents, by changing magnetic flux through the conductor. If we are changing magnetic flux through the conductor, which is in the form of sheet or any solid material, so the loop of currents formed are called eddy currents. So changing, now their core is in the form of sheet, or we can say a solid shape. So changing magnetic flux induces eddy currents in the iron core, causes heating, and due to heating, energy is lost. So this is minimized by using a laminated core, thin iron sheets insulated from each other. So this type of transformer you may have seen near your homes. So these are in the form of sheets, laminated core. So this solid core is divided into thin sheets. Okay, if this is a solid, if there were a solid core, so solid, due to the solid core, large number of eddy currents are produced in this solid core, due to which heating is more, energy lost is more. So this is minimized by using a laminated core, the thin iron sheets insulated from each other. So core is designed in the form of thin sheets. So laminations achieved by stacking thin insulated sheets of steel, as shown in the diagram, increases the electrical resistance. Okay, so this sheet, one sheet will behave as one resistance, and they are stacked. Okay, they will work as they are equivalent to parallel resistances, parallel combination of sheets, parallel resistances. So it will series combination of resistances. So it will increase the electrical resistance within the core, thereby reducing the magnitude of eddy currents. Or we are insulating one thin sheet, one lamination from other, due to which path of eddy currents is broken, due to which energy loss due to eddy currents will be minimized by using laminated cores. Okay, hysteresis loss. So transformers undergo repeated magnetization and demagnetization. Okay, so current is changing, current is going in positive half cycle and negative half cycle, due to which core is once magnetized and in negative half cycle it is demagnetized, as applied field is alternating. Applied field is changing its direction, due to which core is magnetized and demagnetized repeatedly. Okay, so direction of induced magnetic field changes because of change in direction in current, but response of iron core cannot be so fast. This repeated magnetization and demagnetization of the core consumes energy, okay, which appears as heat, and this energy loss due to magnetization and demagnetization of the core repeatedly is called hysteresis loss. So this can be minimized by using magnetic material which has low hysteresis loss, which is soft iron core. So due to the magnetization and demagnetization, energy is lost. So which appears as heat. Okay, and this loss is called hysteresis loss. And we have to use a magnetic material which has low hysteresis loss. That is most common used material which has low hysteresis loss is soft iron core. Okay, so what was eddy currents? Eddy currents was circulating currents that was induced in the bulk of conductor or surface, like surface structure. If there is a sheet of conductor or a solid structure of conductor, not wire. Okay, they are circulating currents, loop of currents. Okay, so they are induced due to change in magnetic flux through that conductor. And we are breaking the path of eddy currents by using laminated sheets, due to which an eddy current loss is decreased. So what is application of transformers? Large scale transmission and distribution of electrical energy over long distances is done with the use of transformers. Voltage in output of the generator is stepped up so that current is reduced, and consequently. So how these transformers are beneficial in the use of power transmission. So when we are transmitting the power, so we can decrease the energy loss, power loss, by stepping up the voltage and decreasing the current. So voltage output of the generator is stepped up so that current is reduced, and consequently transmission loss given by IRMS square. So we are decreasing the IRMS, increasing the VRMS. Okay, so due to which IRMS is decreased, due to which power loss is decreased. So transmission loss given by IRMS square R is cut down or reduced. It is then transmitted over long distances to an area substation near the consumers. Now, this voltage, high voltage, is dangerous. So we have to step down it. So when it reaches the consumer side or consumption sides, this stepped up voltage is stepped down. It is further stepped down at distributing substations and utility poles before supplying of 240 volt, or we can say 220 volt, reaches our homes. Before reaching our home, it is a step down at further distributing substations or consumption sites, okay, to reduce it to value of 220 or 240 that reaches our home. Okay, so this is summary. Power dissipation is maximum at resonance. Transformers work on principle of mutual inductance, and transformers can be step up given voltage if Ns is greater than Np, and step down if Ns is less than Np. If in real transformers, energy loss occurs due to flux leakage, winding resistance, eddy currents, and hysteresis. In power transmission from power plants, step up transformers are used at power generation points to reduce the transmission losses. Step down transformers are used near consumption points to provide usable voltage levels. The standard 240 volt household supply is the result of multiple step down transformations. Practice question you have to do yourself. In a transformer, what is relationship between voltage ratio and number of turns? For an ideal transformer, what is the relationship between input and output power? Why the cores of transformers are laminated instead of using a solid core? A transformer has 100 turns in primary coil and 400 turns in secondary coil. If primary current is 4 ampere, what is the secondary current? Also state whether this is a step up or step down transformer. In an ideal transformer, if the number of turns in the primary coil is 200 and secondary coil is 50 and the input voltage is 440 volt, calculate the output voltage. So thank you. This is all about today's lecture. I hope you enjoyed the session.